All right, the next two lectures are my two favorite lectures. You want to know why?
Why?
Malloc Lab! All right. Hey, come back. Okay, so you guys have programmed enough in C to understand how memory basically works, right? How dynamic memory basically works, right? You call malloc, you get memory. You call free, you give it back, right? And then there's all the fun stuff, like don't give back things you haven't gotten, don't give back half of things. You get the basic idea, right? You call malloc, you ask for a certain amount of memory, it gives you a pointer to a block at least that size. When you're done with that block, you free the block by giving back that pointer, right? It names the block by its address, okay? You understand enough of how memory works to know that the stack grows down and the heap grows up, right? And so as we allocate memory by some magic that we call malloc, the heap will grow. Okay. The allocator maintains heap as a collection of variable-sized blocks, which are either allocated or free. What does that mean? Well, that box that we have there that's called the heap, right, where our dynamic memory is stored, right, where the memory that we get from malloc is stored, right, contains the blocks of memory. What are the blocks of memory in this context? The things that you ask for. When you say, give me a block of size 512 bytes, give me a block of size at least 1024 bytes, and so on, right? Now, if you guys have worked in a language like Python, or Ruby, or Java, right, you had dynamic memory. You can create objects when you wanted them, but you didn't have to do anything magical to do that, right? You just asked for a new object and got one. When you were done, somehow it magically went away, right? In C, it's an explicit allocator, where we explicitly ask when we want something new, and we explicitly ask when we want to give it back. Different than like Ruby or Python or Java, where they're garbage collected languages. We ask when we want something, but then it's up to the runtime environment to figure out when we're done and to take it back. Okay? So an explicit allocator, right, is characterized, by us having to explicitly ask to give something back. And an implicit allocator is characterized by us having to ask, by us not having to ask to give it back. Okay? Our friend malloc. That's what malloc looks like, right? So how does this work? We ask malloc for some amount of memory. What we're really asking for is at least that amount of memory. Dear malloc, please give me a pointer to a block of memory that I can use that is at least this size large. At least. It can be bigger. Okay? But it has to be at least that big. And if it's bigger, you'll never know, right? If you ask for something yay big, and they give you something yay big, you're still only going to use the amount you think you have. So it doesn't matter. It might give you more as a matter of convenience to the allocator. It doesn't help you, right? But sometimes the request will actually be large. So after it finds the block that's right for you, at least as big as you asked, it takes care of whatever accounting it has to take care of, and then returns to you a pointer to that. And that's that. What if? Yes?
If it sometimes returns something larger to you, how come you always get second false if you reference anything outside?
So the question, right, was if malloc, sometimes returns something larger than you asked for, why is it that you, quote, always, close quote, get seg faults if you go past it? The answer is you don't. Sometimes you have a situation where you have an off by one error and it's just not noticed. You happen to get a bigger block. There's no guarantee of a seg fault when you violate a memory boundary in C. Sometimes it happens, sometimes it doesn't, and that's what makes it truly insidious. Because your program can run for years, and you can upgrade your tool chain, right? Upgrade your shared library, the shared library, run the program again. The allocator policy can change, and now your program's suddenly crashing and burning out of nowhere. You could write a program, it could be in use for years and years and years and years. You could be dead and buried. And then one day, they could upgrade the malloc library, start your program, it links against the new library, there's a new policy in place, and instead of giving you this much memory, it gives you something that's less, but still at least what you asked for. And now the program starts rolling over and dying. And now people are cursing your grave. Does that make sense? Yeah.
But if it doesn't always give it to you, then wouldn't it be sometimes give you exactly what you asked for, and it would roll over and die before you die?
Well, look, we've all gotten seg faults.
Yeah.
Right? We've all been in situations we had a memory error and we got a seg fault. Right? Thank you! I've told you guys before, right? I don't know what your religion is, but seg faults are proof. Right? Conclusive proof that in fact there is a God and he loves you. Okay? Because if you get a seg fault, you should say, thank God I got a seg fault. Yes. God is helping me to find my bug. Okay? You don't have to be religious to believe this, right? My grandfather used to joke that there are no atheists in foxholes, right? It's okay when you get a seg fault programming to say, to thank God. It's okay, right? You don't even have to believe, right? Because seg faults are just so wonderful. You guys are looking at me like I'm strange. They are. They're fantastic. Because if you get a seg fault, it stops you and says, you've got an error, buddy, fix it. If you sneak through without that seg fault, your program keeps running with that error. Maybe it finishes successfully by good fortune today, and then the tool chain changes after you're long dead and buried, and now forever they're cursing you because your program is dying and no one knows why. Or maybe it overwrites something important that just happened to be after that in memory, and now, right, you wait forever, right? You wait, and eventually, right, you find out that the answer to life, universe, and everything is 43. Because your program has a bug. Because instead of writing into its own space, it overwrote a variable. Right? So we don't always get errors when we mishandle memory. When we do, we tend to get upset because now we have debugging to do, but the answer is actually really good because we found the problem. Right? Think about it this way, right? Many environments like, let's say Java, right, type check arrays. And that makes programming much safer, right? Because then we find out every time. Right? It'd be nice if we found out every time in C. Then our programs would be more correct. Instead, it's a gamble. Sometimes we find out, sometimes we don't. Just because we get off lucky and our program doesn't generate erroneous results today, doesn't make the program any more correct. Doesn't make it any more trustworthy, right? So we ask for some amount of memory, at least some amount of memory. We get back a pointer to at least that. Right? Let's say that we ask for some amount of memory and it can't deliver that to us. We ask for, 5K of memory, and there ain't 5K of memory to be had. Now what? Well, now, malloc returns null. So the question is, what do we as programmers do if malloc returns null? Anybody know? There's not much we can do, right? If malloc is returning null, that's a pretty dire situation, right? Because what that means is that that malloc itself is running out of memory, so it tries to grow the heap. And it goes to move the top of the heap up, right? And map a new page of memory. And it doesn't have enough. There's no available frame of memory. So then it tries to go to disk and swap in disk as RAM. And there's no more. Like, that's terrible. You're out of RAM and you're out of disk. Oops. Right? The other thing that can happen is you're using so terribly much memory that you've actually managed to bump the heap into the stack or something like that, one of the shared libraries. And now malloc returns null because the page is already mapped. These are terrible situations, right? There's nothing you can really do. I mean, you can try again later. Maybe something was freed. Maybe if you have a bunch of internal data structures and that you can try to do some of your own internal garbage collection and say, okay, maybe there's some objects I can write out to disk or I can throw away or I don't need right now, and maybe clean up your own act. But you have no reason to believe it's actually you causing the problem, right? Because all the processes running on that system share main memory. All the processes on that system share the swap file. So it could be that your process's memory is perfectly well behaved. You're freeing everything when you're done with it. You've got a nice thin memory profile. And somewhere out there's some process that's gobbling up memory, never freeing anything. And there's nothing you can do about it. Okay? So dealing with malloc when it returns null is really hard because your options are pretty limited. Dying with with an error message that says, hey, malloc return null is not necessarily a bad option in many cases. Okay. What happens if you ask for no bytes? Well, then it's going to return null. Okay. If it returns null for any reason, it sets the error no variable to indicate why. Free takes an address. The address you feed to a free has to be an address that was returned from malloc. Okay? So if I ask for an object and I get an object from malloc, malloc returns a pointer to it. I can then give that pointer to free. But if I want to free, let's say, half of something, I can't like move into the middle of an object and pass that pointer to free. Okay? What's going on here is that the memory allocator is using the address of a block as the name of the block and nothing more. Okay? Trying to pass in, right, a pointer into the middle of a block is sort of like taking your name and adding 3 letters to every letter and it meaning the upper half of you. It doesn't work that way. It's just a name as far as malloc is concerned. It's just an identifier. It happens to be the address, but for this purpose, it's just an identifier. Free uses the address to look up the allocation. If you pass in an address that it didn't return to you, it's not the key, so it can't find the value. Okay. Calloc is a version of malloc that allocates and frees. I'm sorry, allocates and clears. That's why it's called calloc. Clear and allocate. It does both. Okay? So it's like a call to malloc followed by a call to something like B0. Zero's the memory. So a lot of new programmers are under the misunderstanding that malloc returns blocks that are zeroed. That's not necessarily true. There is no guarantee as to the initial value of the bytes in the block returned by malloc. Many new C programmers do an experiment like this. They write a C program, and at the very beginning of the C program, they malloc a bunch of memory, and they walk through and they print every byte of that memory. And what values do you think are commonly printed? Zeros. So many intro programmers look at this and say, okay, I've conducted an experiment. I don't know what the behavior of malloc is, so I've conducted an experiment. I've allocated a bunch of memory and I've checked that it's all 0. Therefore, I conclude that malloc must zero memory. That's the right idea. But as it turns out, that's not enough of an experiment. Because here's what happens. Physical RAM is shared by multiple processes. Okay? So if I, as a process, am running in memory, I'm scribbling all over memory. I could be writing private data in memory. If my pages are freed, right, maybe my process ends, maybe my pages are swapped out, and another process gets them, it would be a problem if it could read my memory, right? Medical records, financial data, you know, whatever it might be. So the operating system zeros pages when it gives them to malloc. But malloc is a caching allocator. That is to say, after it gets these pages from the operating system, it holds on to them. And it gives them out in response to mallocs. And takes them back and holds on to them in response to frees. So you won't get anybody else's data. The operating system will zero it before giving it to you. But you can get your own data. That is to say, if you malloc something, scribble on it, and free it. It's now sitting in your cache dirty. The next time you call malloc, you can get a bunch of dirty pages. Does that make sense? So you can't assume that memory from malloc is free, has been cleared, has been initialized. You have to assume it's dirty. If you want it zeroed, you have to do that. Okay? Calloc, clear and allocate, will zero the memory for you. It also has a slightly different interface. A lot of times when we're allocating memory, right, we're allocating something for an array. So I actually want enough space for 100 integers. So with malloc, you say malloc 100 times size of an int. Right? And that'll give you enough space for 100 integers. Certainly don't say 400 and make the assumption that integers are 4 bytes. There's no reason for that, right? Because then somebody reading that code has no idea what the number 400 is for. They don't know it's for 100 integers. Secondly, if the program happens to be compiled and run on a different system, where an integer size is different, the number will now be wrong. Right? So it's not very clear code, right? And it's, in the long run, not maintainable code. It's got a portability problem. Okay? So malloc, if I want to allocate stuff for an array, I'll say I want, 100 times size of int or whatever. 100 times size of struct person. With calloc, it's subtly different in that it actually understands number of elements, size of element. And it does the multiplication for you. So it just takes 2 arguments instead of 1. It's designed to be convenient. So 100 comma size of int. Okay. Realloc, sometimes in life we try to grow a data structure. Maybe we allocated a list of initially of 100 integers, an array of 100 integers. And now we realize, shoot, we have 150 things to store. Okay? One thing we could do is allocate an array of 150 or 200 integers, loop through and copy everything from array 1 to array 2, free array 2, and then point at the new array. Now we're golden, right? Because our pointer now points to a bigger array, and it has all of our data. So what realloc tries to do is make this a little easier. It takes a look at your allocation block, and it asks, is the space after it free? Is enough space after it free? And if so, it grows it. It just changes, the metadata that says the size of the block, and takes the rest of the block, and takes the rest of the block and goes. If, however, there isn't space at the tail, it does exactly what you would do. It goes, finds another bigger block, copies the data over, frees the old block, moves the pointer, returns a new pointer. That's why the syntax for realloc, it's not shown here, looks like the syntax for a malloc, where it returns a pointer. The pointer may or may not be the same as the pointer that you pass into realloc. Okay? For realloc, it takes 2 arguments, the original pointer and the size. The pointer that it returns, right, could be the same if it was able to grow it, or could be different if it had to find a new block. So your form is always going to be something like pointer equals realloc of pointer comma size, where size is the new size. So sbreak, yeah.
How do you know realloc failed, or what happens if that fails?
So a realloc failing would be much like a malloc failing. It'd be the situation where it just couldn't get pages to back up the growth in the heap, or where the heap tried to grow on top of a guard page, a read-only library page, or something like that. And so it reacts just the same as malloc would. It returns a null. Okay. So sbreak raises the heap. There's the point where the heap, right, the top of the heap meets what we call the hole, the unallocated pages above. That's called the breakpoint, BRK. I guess they didn't buy the vowels. Okay? There are 2 system calls that affect or we'll say kernel API calls that affect the breakpoint. One is called sbreak. One is called break. One of them, and I always get the 2 confused, sets the absolute address the breakpoint. Make the breakpoint this. Make the breakpoint this. The other one sets an offset. Grow by this amount. Or technically speaking, I guess shrink by some amount. Okay, a positive or negative offset from the current break value. Back in the day, when it was uphill both ways to class, okay, break and sbreak were actually system calls. These days, they're not. Instead, it uses something called mmap, or memory mapping. That's the actual system call. It memory maps the top of that, and sbreak and break are both wrappers around that. And we'll talk a little more about memory mapping a little later. Here's a malloc example, right? You guys know how malloc plays. I don't want to spend a whole lot of time on this. If I want an array of n integers, I ask for n times the size of an int. Malloc itself returns a void star. In this case, I'm casting that as an int star and assigning it to p. You can read a long discussion, on various internet news groups as to whether or not you should do that cast. There are advantages and disadvantages in terms of what would give you better information in the event of an error. And that's sort of that. At the end, P is the pointer returned by malloc. I can pass P into free in order to free it. That slide's not of interest. Let's talk about this one. What's the purpose of this slide? Here you can see that I'm mallocing 4 bytes, and then 5 more bytes, and then 6 more bytes. Now I'm freeing an allocation, leaving a hole there, and now when I malloc 2, it's reusing space that was previously used. This is an example of where whatever I had scribbled in the bytes over here are still going to be there when malloc returns the pointer we're calling P4. So that won't be initialized to 0 that time. How many of you guys want to use a really, really, really rich banker? Do you want your banker to be really rich? What do you think? You're shaking your head no. Why not? Yeah, where's he getting that money from, right? If you've got a rich banker, right, she's getting that money from somewhere. I don't know that I want a poor banker, but I don't want a really rich banker, right? Well, think about malloc. Right, malloc's job is to manage memory, right? But like any other part of a program, what does it use? Memory, right? So one thing I want from my allocator design is I want an allocator design that's very memory efficient, right? I want it to use as little memory as possible in order to manage memory. But there's another property I want from malloc, right? Let's say you go to the bank, and it's lunch hour, and they're really trying to maximize the returns on your money market account, and so they don't hire any employees. There's only one teller, and the line's wrapping 4 times around the door. Do you say yes? This bank is really financially very efficient. They're not wasting any of my money, barely any of my money on employees. What do you think? No? 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 Time is. What's the problem? I have to wait. Right? So I have 2 goals for my malloc, right? I want it to use as little memory as possible because its job is to manage memory. I don't want it wasting it. I want my memory solving my problem, right? Whatever it is that I wrote my program to solve, I want my memory used as a resource for solving that problem. Flip side is, I want my malloc to run quickly. I want to use all the time available to solve the problem. I don't want my malloc wasting time, right? And so we have a classic time-space trade-off. We might be able to make our malloc run faster if we build data structures that use more memory, but are faster to do lookups and inserts in, right? I might be able to make my malloc run more memory efficiently by using more compact data structures if I'm willing to spend more time searching and inserting things into them. Does that make sense? So we have this time-space trade-off, and we need to balance these. We want good memory efficiency, right? What we call memory utilization, okay? The percentage of memory that's doing what the user wants as opposed to other things. And we also want good throughput, the ability to pump memory operations through without delay. So those are sort of 2 really critical things that we're going to trade off, okay? Utilization and efficiency. Utilization and throughput. And we'll talk more about those in a minute. Now, in terms of the constraints, look, at the end of the day, malloc is there to serve us, the programmers, right? Us. So I should be able to call malloc and free whenever I want. If I want something I should be able to call malloc. If I'm done, I should be able to call free. It should handle any arbitrary sequence of sensible sequence of mallocs and frees, right? I certainly can't free things I haven't asked for, right? That's not what I mean. It can't say, wait a minute, sorry, I'll have that memory for you in 10 minutes. That doesn't solve the problem, right? There's no timeout available, right, in this situation. Malloc has to satisfy our mallocs and frees, give us memory or let us return memory when we ask. in whatever order we ask. It can't start rearranging things. Oh, it'd be more efficient in my data structure if you created this object before that object. Doesn't work that way. Okay? It has to handle whatever sensible set of memory requests we have, right? And it has to do it when we ask. No reordering, no timeouts, nothing like that. It can't control what we ask for. It can't say, you know what? That's too big for right now. Please ask for just half of that. Or it'd be much better for me if you ask for more now and less later. Right? That doesn't work. It can't be a situation where I ask for 1,000 bytes and it gives me 300, and I come back later, it gives me 200. I come back later, it gives me another 200. I come back later, it gives me another 300. It doesn't work that way. It has to give me what I ask for when I ask for it. When we call malloc, if we go back and look at that malloc interface, the argument to malloc is simply the size of the requested allocation. Does it have any idea how we're going to use it? What do you think? No. Okay. Right? It has no idea if it's going to be used for a char or an int or a long or some struct. Right? So it has to return a pointer that's aligned to the largest possible type. Whatever pointer malloc returns has to be aligned to the largest alignment rule, because it has no idea what you're going to use it for, and it could be that thing that requires the biggest possible alignment, right? It can only manipulate and modify free memory. Okay, in Java, for example, right? It has a garbage collector, but it also has compaction. Okay, in Java, you get back a reference. You don't get back a pointer. All right? The way it works in Java is it essentially does the same thing that C does, okay? Basically, when you call new, it allocates a block of memory, and it gets a pointer to that block of memory. But then it has this data structure called the reference table. It's an integer indexed array, an array of pointers. And it walks through this reference table to find an empty entry. It puts your pointer into the reference table, and then it gives you back an integer, an index to that table. That's what a reference is. It's an index into a reference table. The reference table contains the actual pointer. One of the things that this does for us, right, it hides addresses so programmers can't muck with them, but another thing that it does for us is hides addresses so the memory allocator can. So if you end up in a situation where there's 2 bytes here and 4 bytes here and 1,000 bytes here and 512 bytes here, and you need something big, it can shift all of the data, all of the allocations back in memory to coalesce all the open space at the end to make a big thing. Because all it has to do is change the values in the table that you can't see. Your reference is still good. Okay? Malloc can't do that. Okay? Because you actually have the pointer. So when it tells you you can have this space, it really means that space. Not that much space somewhere. Not the data that you've put at that space, but that actual space. Space at that address. Okay? So you can't move things around. And that's because the programmer has the actual pointer, okay, not some type of reference. I talked about the goals of throughput and utilization. Throughput, loosely measured, is the number of operations that the memory allocator will withstand per second. Okay? So if I feed it, 1,000 operations, right, and it takes 1 second to complete those, that's 1,000 operations per second. What's an operation for this purpose? A malloc or a free. Okay, and this is a simple measure of how much time is being wasted by the allocator. The more time per operation, the less operations per time, right? Yeah.
Would allocating a lot of a big data block take longer than a small one?
Yes, that's an interesting question. Like, are all these allocations the same or not? And the answer is not necessarily. Some allocations may be satisfied very quickly because they may be small and anything will do. Some allocations may be large and may require a longer search. So that's why we do this with what's called a workload, some realistic test. Okay, and we compare the results of a standardized workload, perhaps again, being run by several different malloc allocators. And now we have a way of comparing them. So a high throughput is good because it means we're getting a lot of operations per unit time. And that means each of these operations is taking up very little time, which means we're wasting very little time. Right? Programmers don't want to allocate memory. They don't want to free memory. They want to solve some problem, right? Execute some algorithm, and they just need memory to do it. So we want the time spent solving the problem, not on utility work like malloc and free. Okay. Utilization is tricky. Okay? It's really easy for us to say, here's a workload, we got X operations in Y time, so divide, and now I have X operations per second. Ta-da. We know the throughput. But utilization is harder. Okay? Utilization is a lot harder to understand. And the reason utilization is harder to understand is it's really hard to say what we should be measuring and when. All right? We know what the programmer wants. The programmer makes a request. Dear malloc, give me. Okay? That's the request. It's easy to see that if I say, Dear malloc, give me 1,000 bytes, and malloc gives me 4,000 bytes, that there's 3,000 bytes of wastage, right? You guys see that? Because it can never be used. It's been given to me, but I don't even know it's there. That's a type of internal fragmentation. Fragmentation within the allocation. But there's another type of fragmentation, right? Wastage. And that's called external fragmentation. Think about this. If I have a block that's a megabyte large, is it likely that at some point in the near future, I'm going to have a request that can make use of all or part of that? What do you think? What about 100 megabytes large? Is it likely that some future request is going to be able to use all or part of 100 megabytes? What do you think? Yeah, that's a pretty big block, right? Most requests are smaller than that. But let's hypothesize for a moment that I have a block that's 10 bytes large. Is that likely to be reused? No. So if I ask for 10 bytes and get 10 bytes and then free 10 bytes, if that 10 bytes is sitting there in some list, it's just never going to be used, right? Not likely. But it could be used. So I might look at that and say, that tiny scrap of 10 bytes, that's wastage. No one's going to need 10 bytes. That's external fragmentation, right? And then, of course, I could be wrong because the next request could be for 8 bytes. Does that make sense? So it's really hard to understand what we should be measuring if we're trying to understand utilization. And so here's what we do. We basically say, look, the total amount of memory that malloc is using at any point in time is easily measured by the size of the heap. Does that make sense? The total amount of memory that you as the programmer ask for at any point in time is easily measured by the sum of the outstanding mallocs. Simply add up the number of bytes you requested that you haven't freed. Does that make sense? If you have 4 mallocs 1,000 bytes each, you've requested 4,000 bytes of memory. So now I know the total amount of memory that you've requested and the total amount of memory the allocator's using. Does that make sense? We're just going to divide those. For right or for wrong, for better or for worse, that's going to be our simple measure of utilization. The sum of the outstanding requests divided by the total size of the heap. So when we measure the total size of the heap, we're counting like what is there, right? All of the outstanding requests, the amount of memory that's been asked for, all of the extra memory that may have been returned as part of those blocks, any memory malloc itself might otherwise be using, and the entire cache of blocks, things that are ready to be handed out. So our measure of utilization is going to be the sum of the outstanding requests divided by the size of the heap. Is that a perfect measure? No. But is that the one that we're going to use? Yes. Is it a reasonable measure? Absolutely. Right? Because in an ideal world, the total amount of memory used by malloc would be exactly what we asked for. Okay? So when I said the sum of the outstanding requests, that's what the slides here are calling the aggregate payload. What is this word payload? Well, if I ask for 4,000 bytes and you get 5,000 bytes, the 4,000 bytes is the payload. 5,000 bytes is the total size. Heap size is the difference between the beginning of the heap and the breakpoint. Peak memory utilization is going to be what you get when you sum up the payload and divide by the heap size. Okay? If you talk about the peak utilization after a certain number of requests, what that says is I have 10 requests. I look at my memory utilization after each of those requests, okay, and I take the highest value. We talked about internal and external fragmentation. Internal fragmentation within a request. External fragmentation is the scraps left over that are just unlikely to be used. As it turns out, the typical way that malloc is going to be implemented, or atypical way that malloc is going to be implemented, is going to have the memory that you requested sandwiched between a header and a footer. And we'll talk about why. So you'll have a header, the block that you want, some extra padding, and then a footer. That's typically what one of these things looks like. Okay? Oftentimes they're managed in a linked list where the header and footer serve as the previous and next pointers and keep the size of the node. Okay? So in this case, right, it's easy to see internal fragmentation. The header and the footer plus the padding. Why might I have padding? It can take several bytes of management to manage a single byte, right? I wouldn't want to have a 1-byte allocation if it takes me 16 bytes to manage it. I might as well just give you the byte, right? So beyond a certain point, the amount that we would save by keeping the memory exceeds the cost of keeping it. If I have a whole bunch of small little scraps in my available list, and they're not likely to be used, it can cost me time, for example, because I'm searching them. I might as well just give them to you because I'm not saving anything, and I'll make it faster not to have to look. So this internal fragmentation is caused by the overhead of maintaining the heap data structures. That is to say, malloc's own data structures, padding for alignment purposes, okay? Explicit policy decisions. We're just not going to deal with allocations beneath a certain size because they're not worth it. We're going to always return things of at least a certain size. Internal fragmentation is easy to measure, right? Because I can see it and I can point to it. It depends only on prior requests. External fragmentation is harder to measure because I don't know whether a scrap is going to be used or not. Maybe some tiny little block is actually going to be used. So this depends only upon previous requests, whereas external fragmentation, for me to tell you definitively, this is a wasted fragment, I would have to see the program run to completion, never having used it. Then and only then can I tell you that it was useless. So here's a case where you can see after our stream of allocations, 4 bytes, 5 bytes, and 6 bytes, we have 1, 2, 3, 4, 5 bytes free here, and 2 bytes free here for a total of 7 bytes free. Yet, they're not contiguous. So if I try to malloc 6 bytes, I can't get it. I can't return 5 bytes here and 1 byte here because you guys know how arrays work, right? Base plus index times scale. For that to work, they have to be contiguous. Think about our old friend from earlier in the semester, right? Like load effective address. Right? Think about our old, memory address form. Displacement, base, index, scale. It has to be contiguous for that, contiguous for that to work. So when we go to implement malloc, there are a lot of questions we have to answer, right? When someone says free blah and gives us an address, how do we figure out how big that block was to free it? How do we keep track of the free blocks? Okay. If somebody asks for 1K of memory and we decide we're going to use a 4K block. How do we figure out whether we give them all 4K or we give them 1K and save the 3K for later? How do we figure out when the scrap is, too small to be useful? Okay, what's our policy there? Given a whole bunch of blocks that might work, right? If you ask for an allocation size of 1K, a 1K block would work, a 2K block would work, a 4K block would work, a 1000K block would work, a megabyte block would work. A block of any size equal to or larger than the size you requested would work. How do we decide which one to give you? Okay? At some level, one might imagine that if an exact block match weren't found, maybe we'd want to give you the biggest, we want to carve your allocation out of the biggest request, out of the biggest block available. That way, when we take your little piece off, we still have a big block that might be reused. That's a strategy, right? It sounds sensible. Always use the biggest block to leave the biggest chunk free. Maybe that would minimize fragmentation. Right? Another policy that sounds sensible as well, maybe what we should do is give you the smallest block that works. That way we minimize whatever fragmentation we have. We minimize the amount of memory we have unused in our cache. Of course, to do that, we have to be able to find the small block that fits. And that's going to involve a search or sorting to make it easy, and that takes time. Trade-off between utilization and throughput. Does that make sense? Okay. And that comes down to the next question, which is how do we reinsert a free block? Maybe we just stick it at the head of the list, because that's fast. Great for throughput. Of course, the problem is that when we come to allocate memory, now our list is completely unordered. So it's going to be hard, for example, to find the best fit block, because I may have to search the whole list brute force to find it. If I always did an insertion sort and put it in by size, I could sort from smallest to largest, making it really easy to scan forward until I find the first one that works. Now I'm good to go. Or alternately, from largest to smallest, which would maximize the size of the block I left in the list, maybe letting it get reused. We'll talk about these policies in a minute. Best fit, worst fit, first fit, okay? I'll tell you right now that in general, right, worst fit is what it sounds like, right? You don't want to allocate the biggest block for the smallest request, because that just guarantees the biggest block is hanging around in memory for longer. And eventually, in the best case, you've eventually whittled it down to a small piece like you had before. But it was talked about for a while. So let's solve one of these problems. When I say free and give it some address, how do I know what to do? Well, what we do is when we allocate a chunk of memory, there's the payload, the part that we intend for the user to use. Okay? Let's add a header of a known size. So when we allocate memory, let's allocate more memory than the user asked for to ensure that we have at least room for a header. Let's write the size into the header and give the user a pointer after the header. So now the user has a pointer and can just use that pointer. But if the user gives us the pointer, we can subtract the size of the header, and now we have a pointer to our header. Does that make sense? What do you guys think? So now, when the user says free this allocation, we go to the pointer, we back up by the size of our header, and now we know how much memory to free. That's also why it has to be a pointer that we gave the user, that was returned by malloc. It can't be some random address. Because if the user gives us an address in the middle of this, and then we back up by the size of a header, is there any useful information there? No, it's not useful to the user, they're giving it back. It's not useful to us, it doesn't have a size. Okay. Does this cost us something? Sure, right? The header takes space. It's a type of internal fragmentation or wastage. Okay. If we use this, what we actually have here is a type of linked list. Right? I can walk through, and if this is an allocation, and I know its size is 5, I can move 5 bytes, and that brings me to another block. And if I know its size is 4, I can move by 4 bytes, and it brings me to another block. And if I know its size is 6, I can add 6 to the address, and it brings me to another block. And if I know its size is 2, right, I can move by 2 bytes. Make sense? Okay. This your book calls an implicit list. The pointers are implied by the size. Does that make sense? The size of each block serves as an implicit pointer to the next block. Do you see that? Now, to make this work, because we're initially dishing things out, right, but then we're getting memory back via free, we need to understand what's a free block, that is to say is available, and what's a block that's in use. So in addition to the size, our header has to have a flag that says available or not, free or allocated. Does that make sense? So now we can walk through our list and look and ask 2 questions. Is it big enough? And if so, is it available? Make sense? Or alternately, is it available? And if so, is it big enough? And we can walk through until we find something that suits our needs. If we're looking for the first fit, we can find the first one that's big enough. If we're looking for the best fit, we can walk through until we find the smallest one that's correct, remembering it as we go along, and then come back to it after we finished our search. Okay? If we're trying to do the worst fit, again, we walk through until we find, keeping the worst candidate in mind until we get to the end, and then use the worst one we found. Yes?
What does the end of moment list look like? Is it just a pointer to a question mark?
Right, so when you're implementing this, you need to have some sentinel value that says you're done. Does that make sense? The other thing you can do is if you know the size of your memory, then you know that if I'm at this pointer plus this much, I'm past the end of my memory. Does that make sense? Because, if you know how big memory is, and you generate a pointer that's outside of that bound, you know you're done. The problem with an implicit list is that if I'm looking for free blocks, I have to walk through a long list that has both free and allocated blocks, right? That's one, I shouldn't say the problem, that's a big problem. Make sense? Another problem is my list is necessarily ordered by address. I have to search this list from the block with the lowest address to the block with the highest address in order of increasing address. I can't do an insertion sort by size, for example. I have to stick with this ordering from lowest address to highest address without considering other possible orderings or even whether or not the block is allocated. A so-called explicit list has an explicit pointer to the next block. We're no longer using the size. We're no longer using the size as an implicit pointer. We're keeping it there, and we'll talk about why, but now we're having an explicit pointer in addition to the size. So now, my linked list might include, for example, only things that are free, skipping past the things that are used. That'll make a search much faster. If I'm looking for a block that I can use, it doesn't make any sense to look at those that are already used. It'll also let me order things in different ways. I might choose to order these pointers from largest to smallest, from smallest to largest. Does that make sense? Yeah. Okay. The third method is a segregated list. We'll talk about this, but the idea is that if I just have one list, it has things in it that range from itsy-bitsy to huge. And it makes no sense to search through all the itsy-bitsy little things if I need something really big. And if I need something really small, right, probably I don't want to carve it off something huge if I have something really small. So it's the idea that we create a small, medium, and large classes of size classes. Or, super small, small, medium, small, medium, medium, large, large, and huge, or whatever. I create lists of several different sizes, and I figure out which list to look in. That way I'm only looking at things of approximately the right size, and my search goes faster. Of course, I can only sensibly have a certain number of these lists, right? Because at the extreme, I have a 1-byte list, a 2-byte list, a 3-byte list, a 4-byte list, a 5-byte list, a 6-byte list, a 7-byte list, an 8-byte list, a 9-byte list, a 10-byte list. And then it gets really complicated to figure out which list I should be using. It'll take more time to figure out which list I should be using than it would have been just to do a search. What's that?
Then you'll have to keep track of where the lists are.
Yeah, just the overhead, like keep track of where the lists are. It's painful. Okay. The other thing I can do is I can do something other than a list. Right? I can build some type of AVL tree, splay tree. Tell Danny I said hi. That didn't get as much of a chuckle as I thought. Okay, who am I talking about when I say tell Danny I said hi?
Slater.
There you go. Who's Danny Slater?
Display trees.
He's the guy who invented splay trees and amortized analysis. Why do I think that you guys might know him?
251.
Teaches 251.
451.
451, although you haven't gotten there yet. Okay. So today we're going to talk about implicit lists. Next class we're going to talk about the more advanced lists. Each of these blocks is going to contain the payload. Okay? The memory that the user actually asked for. And the user is going to get a pointer to the payload. It's also going to contain a header. The header has to tell us the size of the block, so we can skip past it to the next block. It also has to tell us allocated or not, so we know whether or not we can use it. Here's an observation. Does it make any sense for us to allow a minimum block size of 1 byte? No, it's going to take way more than a byte to manage a byte. I might as well give it to you. Hypothesizing for a moment that my minimum block size is 2. And in reality, it's going to be much larger than that. But just for the moment, hypothesize my block size is 2. Minimum block size is 2. Am I ever going to have a block that starts with an odd address? No. Think about it in terms of alignment. When I call malloc, do I know how it's going to be used? So I have to assume it's going to be the largest possible type, right? So if I have 64-bit alignment, it's going to have to begin in a multiple of 8 bytes, right? 64 bits. That means it can't be odd. My ones place is always going to be 0, right? It can't have anything in the twos place, right? Because then it wouldn't be a multiple of 8. It can't have anything in the fours place. So those 3 bits will always be 0, right? Knowing that, it makes it really easy to get a few extra bits, just for accounting purposes. Because I can take whatever size I have here, right, and set that bit to 0. And I have the correct answer. So I can just steal a low order bit or 2 or 3 to, or whatever. So that's where I get that bit from. I just steal it. And then my payload may be padded. Why? A, for alignment purposes. B, just because the user requested something too small. C, because I'm giving users only things that are multiples of a certain size. A so-called power of 2 allocator always works by dividing the allocation in half. It makes it easier to coalesce, to put the blocks back together in the end. So if we look at this diagram, what do we see? We see the size, and then a 0 for free or a 1 for allocated. This thing has 4 bytes per block. So this is 8, is 2 blocks. This is 16, it's 4 blocks. This is 32, it's 8 blocks. This is 16, 4 blocks. And so you can see now my pointers, my explicit pointers, my implicit pointers, right, are following my size. This is 2, this is 8. 2 blocks here, yink. This is 16, yink. This is 32, yink. This is 16, yink. You see that? And then here, if we look, this points at a block that size is 0. And I forgot who was in the back that asked. That's serving as a sentinel to show us that we're done. Now, if some user asks me for some amount of space, 4,000 bytes, 5,000 bytes, 7,000 bytes. We talked about the fact that we have this list that's ordered by address. So we have no idea where we might actually find the best possible block. Okay? We also have to think about what is the best possible block. Maybe there's an exact fit, in which case that's the best answer in some sense, right? but maybe there's not. Well, if I want to search for the best fit, the block that's closest in size without going under, since my list is ordered by address, because it's ordered simply by size, by the size pointer, which takes us through memory in address order, I would need to search the entire list. But then after I would search the list, I'd find the smallest block that's not too small and use it. So I would return the smallest possible amount of memory to the list. Okay? This would be very good for utilization, right? This would mean that I'm taking out large blocks of memory, putting in small blocks of memory, right? Decreasing the amount of external fragmentation as I go. Cool. The problem with it is it involves searching the whole list. So utilization, good. Throughput, bad. Okay? Another possibility is so-called first fit. I just start at the beginning and charge forward until I get the first block I can possibly use. It may be a good block. It may even be the best block. But it may also be the worst block. Does that make sense? The worst fitting block. But what it has in its favor, at least initially, is speed. Once I find something that works, I stop. I don't have to keep searching the list. Okay? And then we talked about the possibility of worse fit, which is really silly. Right? That's like saying I want to leave as much extra memory unused as possible. Okay. Well, so for a first fit, I simply start out at the beginning and I search until I get the end. And I keep searching as long as it's too small. Okay? How do I move from one block to the next? Well, I have my pointer, and I need to say basically what you would look at in terms of freshman programming is P equals P arrow next. Right? Step to the next node of the linked list. Well, where do I find my next pointer here? It's my pointer, right, minus my size. So I have to, plus my size. So I have to back up to get to my header, and then find the size and step forward by that. So I take my pointer, I back up by the size of the header, right? That gives me the pointer to the next block. I add that to my current pointer, and now I'm pointing at my next block. Yes?
Isn't that masking out the flag bits as opposed to moving back to the header when you and with -2?
So I'm...
P points to the header, not to the start of the usable memory.
Oh, so let me take a look at the code. I may have just, I sort of glanced at it sideways. Okay, so P is my pointer in memory. I'm adding to it. Oh yeah, so what I have here is the only thing in my header, right, is going to be my size. I have nothing else in my header right now. So when I dereference P plus dereferencing P, right, in theory gives me just my size, the amount I should step. But I have the allocator unallocated flag, right? Which is I'm currently, using the ones bit for. And so here, as you observe, that's exactly right. I'm masking that out so that I actually get my real size. Thank you. Who? You? Thanks. I glanced sideways at the code back at you and didn't quite grab it in that sideways look. Sorry about that. Now, if you're doing what the book calls first fit, you're actually being really silly about it. Because what happens is, if I always start at the beginning, okay, I'm going to take the big chunks out of the beginning and then start over at the beginning again. And now there's no more big chunk. So now I have to search farther. Then I start back at the beginning again. And I've already taken out some chunks. And so what happens is all the small chunks start find their way to the beginning. And I'm just walking past them longer and longer and longer and longer until I actually get there. Does that make sense? So the easy thing to do is make it a circular search. Start out at the beginning and search until I find something and just leave the pointer there. Now search until I find something, leave the pointer there. Search until I find something, leave the pointer there. Search until I get to the end of the list, and then just reset my pointer back to the beginning. And the idea there, since everything is just simply ordered by address, when things are freed, they're freed in arbitrary places. And so by the time I get back to the beginning, things have built back up again. I have decent sized blocks again, and I can scan forward again. Make sense? Best fit, right, in the case of an implicit list, it's sort of unfortunate because my list is address ordered. So if I want to know the best fit, I have to search the entire list first, keeping the best I've seen so far, and then go back and use that. So it improves utilization, but at a cost to throughput. Okay. All right. So what's going on here? We've got a couple of inline functions. What's an inline function? Yeah.
Every time you call, it'll just place itself there.
Was that?
When it's behind, it'll just place itself wherever you called it, the entire code.
Yeah, so as programmers, we use functions, right, because it helps us understand the code better, right? It lets us factor our code. It makes the code more readable because we have a function name in place of a complexity, right? And then it lets us go back and dive into that complexity. It allows for code reuse. We can write something once and use it many times. But the problem with functions, as you guys learned, is there's an overhead associated with them. You have to jump somewhere else in memory, which can really mess up your caches and things like that. Okay? So an inline function, got to sneeze. Thank you. An inline function gives the programmer the benefit of functions in terms of it still allows the code to be readable, still allows us to name a chunk of code, still allowed code reuse, but avoids the overhead of having to jump to the function by just blobbing that code down every time it exists. The downside is that the program can get big fast, right? If it's a big and complex function and you inline it, there are going to be a whole bunch of copies of that function in your code. So inline functions are designed as a way of having small functions repeated, where the size of the function isn't worth jumping, because you're not saving much. Okay? So here we just have a function called isBeforeEnd. And now I pass in some block, and I ask the question, is that block less than the heap? Right? My breakpoint is here. I ask the question, is that block between the beginning, between the beginning of the heap and the breakpoint? Okay. So if it's greater than 0, it's fine, right? The only test we really have to have is it less than the breakpoint? Here's another function, isInHeap. Okay. Well, is it less than the breakpoint, and is it greater than where the heap begins? This lets us now exclude, for example, the text area where the code is. It forces us to start at the beginning of the heap and less than where the heap ends. You guys know requires from 121. I won't repeat that. If you're a 513 student, not a 213 student, then don't worry about requires. It's a 121 thing. And so we have isBeforeEnd, isInHeap. Okay. Here's another way of doing this. This is not another way of doing this. This is, here's a test for isAllocated. Remember, we're using the low order 1 bit to determine allocated or not. So here you can see we take the block and we end it with a 1. If the 1's bit is set, right, allocated. If the 1 bit is not set, not allocated. Get length of free block. Well, how do we figure out what the size is? Well, we return the size. Okay. What? Why am I sad? Yeah. Yeah, we need to mask out that 1, right? What should this read? There's several ways we can get at this, right? Ultimately, we need to eliminate a 1. So what can we mask it with? We can end it with all 1s and a 0, something like that, right? Yeah.
If it's required to not be allocated, though, then we'll just won't be guaranteed to reset to 0.
So this does require. Okay, so if we're using requires, I'm sorry, I missed that. Yep. Okay. Sorry. Yeah. If we are, so the requires is making sure if you're doing the 121 thing that it's an allocated block. So now, in fact, If we know it's allocated, if we know it's not allocated, and that's guaranteed to be 0, we can just return it. We've already done the test there. Good call. Get the length of the block. There we go. Okay. Now, because this is not guaranteeing that the block is used or not used, now we have to deal with that. Get the next block. Okay. Block plus the length of the block. First fit now is sort of pretty, right? While it's before the end and it is allocated, or the length of the free block is less than the length, move forward. So when we get to the point we have something that fits, we're done. Okay. Now, the question now comes up, what happens if I find a block that works and I have some stuff left over? Okay, like here, I'm looking for 4 bytes, and I find this thing that has 6 bytes. Let's say I want to claim the 4 and give back the 2. Well, this is actually fairly easy. I just write a header into this block and reset my size. Now my list is perfect. Does that make sense? This is my original allocation. I add the header for the next block, and then I reset my size. Ta-da. Okay. All right. Let's say we want to free a block. Well, the easiest thing we can do is just whack the allocated bit. Simply mark it as unallocated. What's the problem with that? Well, this is false fragmentation. It looks like I have a block of size 4 and a block of size 2. Oopsie. What I want to do is be able to go back and reset this to 6, right? Look at this and say, okay, what's going on with the block before me? Oh, the block before me is also free. Reset to 6, make this back to one big block. I also maybe want to be able to look after me and say, hey, is the block after me free? Yes, it is. Reset my size to encompass that. The problem with what we've got here is that we only have a header, so we can only move forward. Do you see that? Okay. To deal with this, I want a header and a footer. Now I can move forward and backward. Because if I start out at my header and I back up by the size of the footer, I now have my predecessor's size. And if I know that my predecessor's size is 4, I can back up to get to its header. Do you see that? So to move forward, I use my size, gotten by backing up to my header. To move backward, I back up by the size of my header plus the other one's footer, right? A header plus a footer, yink. That gives me the size of my predecessor, and now I back up by that size. Now I can move forward and backward. This lets me look left, coalescing if possible, then look right, coalescing if possible. And that's the most I'll ever need to do. I can have a constant time coalesce by looking left and then looking right. Done. Okay? As long as I coalesce at every opportunity, I can do it in constant time. Left, right, done. If I delay, a lazy coalesce, then what I might have to do is go through my list from start to finish, coalescing as I go. Does that make sense? Because then I haven't done it as I go, so I can have work built up. Okay, and we can see the header and the footer can be symmetric. All right. I'm not going to walk through all these cases because it's just freshman programming again, right? Left, predecessor, and successor in a linked list. We call the header and the footer boundary tags. Why? They come before and after. What's the disadvantage? Boundary tags take space. They waste memory. That's internal fragmentation. Perhaps it can be optimized. All right. So key allocator policies. We need to think about whether we want first fit or next fit or best fit or worst fit. Right? How we want to balance utilization and throughput. The classic time-memory trade-off. We want to think about our splitting policy. If we ultimately decide on a block that's bigger than what the user asked for, do we give it all to them? Or do we keep some because we might be able to use it for later? Sort of what's the smallest thing we're willing to keep in a list? We want to talk about our coalescing policy. Do we do it immediately, which gives us a constant time coalesce? Or do we say, you know what, we want to get through as much as we can, as fast as we can, so we're not going to bother? The flip side of that is that when we coalesce, we can end up having a long delay because we have to walk through everything. Furthermore, it can actually slow us down if we end up with a lot of wasted space, right? A lot of extra blocks that we can't use. Our searches can get longer. Hint, we almost always want an immediate coalesce, a constant time coalesce. Implicit list, we use the size of the pointer. Okay? Linear search is the worst case. We could have to walk through the whole thing to find a block that will work. We can do a constant time coalesce by looking left and looking right. We can affect the time-space trade-off by deciding what our policy is going to be. First fit, best fit, worst fit. In reality, it's not used in common mallocs and frees. It's just not efficient enough. We're going to learn next class how we can get better control of this to balance it. Using the explicit list, the extra set of pointers so we can order things the way we want. And generating several lists of different sizes so we can search only a more appropriate set of things. Avoid searching all the small stuff if we're looking for something large, for example. But it is a good basis for understanding how malloc and free works. And it can also be used in simple special purpose allocators. Any questions? Yes?
When is malloc actually used? Because the website says two different things.
Okay, send me email and I will take a look. I would go with what the website says, not Autolab.
The website says, on schedule it says it's due April 9th, and then if you go to the labs page, it says it's due April 14th.
In our start yesterday, they were talking about this, and once the TA association sent out an email, they would.
Yeah, there was a whole discussion last night on the staff list of this, and I'm trying to remember where it ended. But it ended with changes to both the due date and the checkpoint. And I think Seth was the one who was point on sorting that out. And so I think there'll be an update to the website tonight. The answer is, we're not cheating you on time, we're just trying to de-interfere Carnival. That's our goal. Try to make sure you can focus on Carnival during Carnival time and focus on malloc during malloc time. Have a great day, everybody.